Okay, so applications of linear systems is very much like the packets we've been working on, and you're going to notice a lot of commonalities between these. Things like finding the break-even point. Finding the break-even point is very much like our profit, income, expense equation. This problem, a fashion designer makes and sells hats. The material for each hat costs $5.50. The hats sell for $12.50 each. The designer spends $1,400 on advertising. How many hats must the designer sell to break even? So if X is the number of hats sold, and look, we're even defining variables like we would previously. Y, number of dollars of expense or income. So Y is like and we're writing it like that because we want expense and income to be equal. That's what we mean by break even. So Y is sort of both expense and income. So if we're writing an equation for the expense, we would write Y equals 5.5, the $5.50 on the material, plus X for the number of hats, plus 1,400 on advertising. Our other equation would be Y equals 12.5x for the amount of money that's made doing that. Okay, so this is the income equation, and this is the expense equation. Since we're interested in where these two things are, where y is equal in these two things, we can set these equations equal to each other and get 5.5x plus 1,400 equals 12.5x. When we solve that, we find that x equals 200, so they would have to sell 200 hats to break even. Another part of this chapter, however, is something we only talked about briefly in our packets, and this is the idea of constraints and viable solutions. So there's a problem in here about identifying the constraints and viable solutions in a local zoo problem. And the problem reads like this. The local zoo is filling 2 water tanks for an elephant exhibit. One water tank contains 50 gallons of water and fills at a constant rate of 10 gallons per hour. The second water tank is a 29-gallon tank and is filled at a constant rate of 3 gallons per hour. When will the 2 tanks have the same amount of water in them? So basically, water in the tank, Y, is going to be equal to, in one case, 10x plus 50, and in the other case, 3x plus 29. Set those two equal to each other, we get 3x plus 29 equals 29 equals 10x plus 50. Subtract 3x from both sides, subtract 50 from both sides, and we get 21 equals 7, negative 21 equals 7x. Divide by 7, divide by 7, x equals negative 3. The conversation then is around this answer. Is this a viable solution? Can we have negative 3 amount of time? The idea being like negative 3 hours. Maybe in some scenarios, but not this one. So this is not a viable solution because we're not going to be traveling back in time. So that's the kind of thing to look out for. Think about the world of the problem and compare the world of the problem to the kind of answer you're getting. If you're getting an answer that doesn't make sense in the world of the problem, that's what we consider a not viable solution. One type of problem we really didn't see in our packets is this idea of wind or current problems. Wind problems and current problems involve usually travel of some sort, either boats on water or airplanes through the air, and they have to deal with this idea that wind speed is going to be consistent, but sometimes it's going to be working for you like a tailwind or against you like a headwind. So here's an example problem. A traveler flies from Charlotte, North Carolina to Los Angeles, California at the same time. Another traveler flies from Los Angeles to Charlotte. The airspeed of each plane is the same. The ground speeds are shown below. What is the airspeed? What is the wind speed? So here's the idea. The ground speed of the one airplane going from LA to Charlotte is 550 miles an hour. The ground speed going from Charlotte to Los Angeles is 495 miles per hour. The equation for this is essentially airspeed of the plane plus wind if it's a tailwind, meaning it's pushing you from behind, gives us this one equation. And the other one, you just subtract the wind because it's coming at you and it's slowing you down rather than pushing you from behind. So if that's the case, we can actually solve this using our elimination method, right? A minus W equals 495. Add these equations together, we get 2A equals 1045 divided by 2 divided by 2. The airspeed, therefore, for both these planes, because it says in the problem they're the same, right, is 522.5, which means that the wind speed is 27.5. Okay, so it's just a matter, it's a different setup than we've seen before, but it's this idea that speed of the plane plus the speed of the wind, if it's a tailwind, it gives us this. Speed of the plane minus speed of the wind, because it's a headwind, gives us this. Solve using elimination. I think for the most part, you're going to find that these problems are actually easier than the ones we face in the packets. Give them a good try, and we will talk more about them tomorrow.